Really? And he was like, you can't do it, yeah. And the series like the exact opposite. She's like, oh yeah, you're gonna have an OChem quiz on Thursday, that's like 30 points. And then the only accommodating thing she said today, thank God she said this, she was like, okay, so I kind of noticed y'all kind of bombed the last exam, which is fair. So I'll do all the cutoff by 3%. So like an A in the class now is like 79%.
All right.
And I was like, oh, thank you, thank you, thank you.
What is that?
118A.
Oh, that's not the next one.
She's the only one teaching 118A.
Really? Like,
Is it really last time?
I mean, I heard she's good. No, I don't.
It's like,
I heard she's hard.
I don't know.
No one, she's like, no one's It was so frustrating though, before I signed the exam, I had like a solid A in the time. I was like, I'm still there, this is great, it's like 2 weeks left of the quarter, I'm all good, I'm set. She puts in the exam grade, my grade goes out by like 5%, amount of B plus, and I'm like, oh.
Very much A territory.
No, but I was like, this means I need to do so amazing on a series final because it's 40% of my grade. I was like, what? I was like, why did she do that? I don't know.
It's too hard.
I feel like she's very hard to read. Like, she's hella nitpicky. Like, if you literally just forget to put like a negative sign of oxygen, it's like 5.
Is the are the tests like formatted like how just
Well, yes. Well, no, her first exam was like literally all free response, which is hella nice because there's a lot more work. But because the TA strike, she made the second exam all multiple choice, but that means the questions are like each worth 5 points. There's not a lot of questions to begin with.
Which I lost.
And then it makes it insanely difficult and like super icky and stuff that you didn't even talk about. And I was like, no wonder we all paused the last exam. We didn't even teach this stuff.
yeah, that's like how everything like the extra office on it.
Her officers aren't even that helpful. I mean, I'll go tomorrow. But they're
So many videos I have to watch a lot of them. I mean, it's good. It's yeah, it's all good.
like,
the last lecture. To me, it's like I thought this was nice, but I didn't do
that's also like how we done it. Like if people just need to like need a recap, just watch the last lecture.
All right. That's all.
I do.
So probability.
Everyone's favorite thing.
I know, right? So we talked a little bit about probability, and the thing I would remind you all of when it comes to probability, the main, like the biggest thing you need to remember is the probability. The way we calculate some probability, like for example, the probability of A is just the number of ways that A happens divided by the total number of things that can happen. I know it's very generic. That's kind of the point, is that if you can keep this idea present when you're thinking probability, you will have somewhere to go at least. Now, that said, there's a lot of different things we can do. Let's talk about. Sure, we've done that. So we talked about probability. Let's talk about conditional probability, because that's something I imagine you've talked about. That I definitely saw in your homework. So conditional probability. Let's look at some examples. So for example, sure. So let's say we draw 2 cards from a deck. We want to know what's the probability that the second card is a heart. Given that the first card is. Well, there's a couple ways to calculate things like this. So let's say that let's use some terminology or some notation. Let's say A is the event that the first card is a heart. B is the event that the second card is a heart. The notation for what we're trying to calculate is the probability of B happening given that A has happened. That's how we write conditional probability. And the way we calculate it is it's the probability that both B and A happen, or the probability of the intersection, divided by the probability that the given thing has happened. Probability of A. Now, there's kind of 2 different ways of seeing how this works. One way is to actually calculate this probability, which is not like the most intuitive way of doing it. The other way is to kind of think about what you're left with after the given thing has happened. So let's think about the second way first. So the quote unquote intuitive way. So let me ask you. We drew a card. The first card was a heart. Okay, now that that's happened, what are we left with? We're left with a deck of how many cards and how many of them are hearts. Great. There's a 12 out of 51 chance of drawing a heart from the remaining 51 cards. So this is going to equal 12 out of 51. Now that's not exactly what this calculation is. I mean, it is, but there's a little bit more to it here. So if we were doing it this way, the probability of A, the probability of the first card is a heart, is, well, there's 13 hearts out of 52 cards. The probability of A and B, or B and A, the probability that the first card is a heart and the second card is a heart, well, that's going to be, let me make sure I do this right. Yeah, it's going to be 13 out of 52 times 12 out of 51. Interesting. Oh, that's what the question. Okay. So then if we divide these together, the probability of A intersect B divided by the probability of B is a little more complicated looking, but it's the same idea. 13 out of 52 divided by 13 out of 52 times 12. Oops, let's see. I've got, I got that a little bit backwards. Sorry. 13 out of 52 times 12 out of 51 divided by 13 out of 52. And those cancel and you get 12 out of 51. So either way you slice it, you are going to end up getting 12 out of 51. It's just sometimes it's easier to kind of think about what you got versus other times it's easier to not. Sometimes this calculation is actually the way we have to go because of what we're given. Let's look at some more examples here. I should say a few more things about this formula for 1 second. So just so you all see things. So this calculation comes up in a lot of different ways. You can either see it like this, the probability of B given A is equal to the probability of B and A over the probability of A. There's another way of writing this. Oops, sorry. We can also write it as the probability of B given A times the probability of A is equal to the probability of B and A. This is another way of writing this equation that sometimes is useful. The reason we're talking about this is really because this is the general way of how we calculate conditional probabilities. If, on the other hand, A and B are independent, something else happens, something related. So if things are independent, it means that knowing that one of them has happened doesn't affect the probability of the other thing happening. Right? I'm never going to come up with examples of this, but I'm like trying to think of something, right? It'd be like something totally unrelated happens and it doesn't affect the probability that I went for a run today. Right? Like you slept in, that doesn't change the probability that James went for a run. The way we write that using this notation is that A and B are independent if I prefer to write it this way. The probability of B given A is equal to the probability of B. Knowing that A happened doesn't change the probability of B happening. So probability of B happening, knowing that A happened is the same as probability that B just happened, not knowing anything. And there's three ways of writing this. Probability of A given B equals the probability of A, or my least favorite way of writing it, the probability of A intersect B is equal to the probability of A times the probability of B. So if any of these things are true, well, first of all, if any of them are true, all of them are true, right? Each of these are equivalent to the other. But if any of them are true, that means the events are independent. And what I want you to notice is the difference between this calculation versus this calculation. They're definitely different things. Here, calculating the probability of B given A gives you this. Whereas here, if they're independent, calculating the probability of B given A just gives you the probability of B. Yeah. So you could say they're dependent, but really the idea is you can calculate it this way, whether or not they're independent or dependent. The idea is that when you calculate it this way, whether or not they're dependent or independent, if they are independent, it'll equal the probability of just B. So it's not so much that this is how we calculate the probability of B given A, it's that if this probability, which we calculate in this way, happens to equal this, then the events are independent. Yes, it would be wrong to, it would be definitely wrong to do this all the time. Because that would be assuming that events were always independent, which is not always true. Let's look at some examples. Well, in fact, so for example, so let's look at this example. What's the probability? I always hate writing out all the events. So let's say that A is the event of drawing a queen from a deck. And B is the event of drawing a face card. So first of all, what's the probability of drawing a queen? Well, there's 4 queens in the deck, there's 2 cards in the deck, 4 out of 52, which you could reduce to 1 out of 13. Okay. What's the probability of drawing a face card? How many face cards are there in the deck? Jacks, queens, kings, 12 of them. Or there's 3 ranks that are face cards out of 13 total ranks. So you could start with 12 out of 52, or you could say it's 3 ranks out of 13 ranks, which is what that reduces to. But now the question I want to ask is, what's the probability? Let me make sure I write this the right way. That's a dumb one. Sure. Sure. So what's the probability of drawing a queen given it's a face card? Well, we can calculate this one of 2 ways. Let's do it the non-intuitive way first. The probability of being a queen and being a face card divided by the probability of just being a face card. Okay, so how can a card be a queen and a face card? Well, it has to be a queen. So there's only still 4 out of 52 ways we can be a queen and a face card. One way to kind of think about this is being a queen is a subset of being a face card. So if you want to find the intersection of A and B, it's really just A because A is wholly contained in B. If you're drawing a Venn diagram of this situation, this would be all the cards in the deck, and here would be the face cards, and here would be the queens. which are all contained inside the face cards. So that means that's an A right there, in case you couldn't tell, sorry. That would mean the A intersect B is just A, because it's the overlap. And then the ways of drawing gosh, my brain one of a face card is 12 out of 52, and this reduces to 4/12, which is 1/3. The more intuitive way I think of saying this is, okay, we've drawn a face card. There's 12 of them. From those 12 cards, what's the probability of drawing a queen? Well, there's 4 queens out of 12 cards. So the other way of saying is, 4 queens out of 12 face cards. That's going to be 4/12, which is 1/3. When I think about a conditional probability, I think of the given condition as kind of reducing the sample space I am working with, so that my new kind of space I'm living in is B, or whatever the given thing is. Another way to, the other thing I want to say about this is, note, these events are dependent or not independent. A and B are dependent. Because knowing that one of them has happened affects the probability that the other one has happened. Right? The probability of drawing a queen on its own is 1 out of 13. The probability of drawing a queen knowing that you had drawn a face card already is 1 out of 3. Since those are different, these events are dependent or not independent. Yeah. Another way I like to think about this probability here, so back actually up here for just 1 second. When I think about this formula, graphically, I'm thinking of this sort of Venn diagram situation. So I'm thinking of, here's A and here's B. And here's A intersect B. And what we're saying is, we're trying to find the probability of B given A. We're assuming that A has already happened. Right? We're in the land of A. And then, oops, covered up. If we're already in here, we're trying to find the probability that B happens, given that we're already in this reduced, smaller space. Well, it's only this overlap part that is where B happens. So we're taking this overlap area and dividing it by the total possibilities, which is just the stuff in the A, not the whole sample space anymore. Okay. Let's see then. I don't want you. I like my questions are not. I like my examples are right, but they're fine. We'll look at another card example, and then maybe we'll look at some examples as well. So let's look at this next example. Again with the cards. Draw 1 card from a deck. What's the probability that it's a heart given that it's a 7? So again, if we label things, we call being a heart event B and being a 7 event A. We're asking, this is important. We need to make sure that we write this in the right way. So what's the given thing? The A or the B? Okay, so that's the thing that goes last. So we were trying to find the probability of B given A. I personally like to just do it kind of the shorter way. So if we know that we are given that it's a 7, right? Well, here, great. Here's our whole entire world. I should really just not write omega. I should write A. A is just the 7 of hearts, the 7 of clubs, the 7 of diamonds, and the 7 of spades. That's my whole entire sample space as far as this question is concerned. From those 1, 2, 3, 4 possible things, how many of them are hearts? Right. So the probability B given A is 1 out of 4. We could also calculate it the longer way. We could calculate it as, sorry, B given A, apologize. the probability of A and B divided by the probability of A. The probability of A and B, probably of getting a heart and a 7, is 1 out of 52. There's 1 7 of hearts out of all 52 cards. Right? It's not conditional anymore, so we're back to the entire sample space of all the entire deck. Divided by the probability of A, which is the probability of drawing a 7, well, there's 4 7s in the deck. So that's 4 out of 52. And not surprisingly, this reduces to 1/4. Follow-up question. Is the so are A and B independent? Well, let's ask ourselves, is the probability of B given A the same as just the probability of B? Well, we already calculated one of them. This is equal to 1/4. Just calculated it. And what's the probability of B? What's the probability of drawing a heart? Well, there's 13 hearts out of 52 cards. That's equal to 1/4. So these events are independent. Knowing that the card is a 7 doesn't affect the probability that it's going to be a heart. If I don't know what kind of rank the card is, there's a 1 in 4 chance of getting a heart. If I do know that the card is a 7, there's a 1 in 4 chance of getting a heart. Either way, there's a 1 in 4 chance of getting a heart. So knowing that A has happened doesn't change the probability of B. So those events are totally independent of each other. Yeah.
For independence, is it always that it equals the probability of the that to B, or?
It's always the probability of the thing given the other thing equals the probability of the first thing. So you can do it this way. You could also have done it this way. And then my least favorite, you could also have done it this way. The reason this last one is my least favorite is because I feel like it has less meaning. These two ways of writing it say something to me. This says, oh, the probability of A knowing that B happens is equal to the probability of A. So knowing that B happened didn't change anything, so they're independent. Whereas saying that the probability of A intersect B is equal to the probability of A times the probability of B, that just feels less like it has a nice interpretation for me, which is why I don't like it as much. Sure, let's look at some not card examples. And I should say, if there are specific homework questions you would like me to look at, I'm also happy to do that. I just haven't looked at them that closely. But let me look at this example here. Whoops, let's get the pen going the right way. Family has 2 children. One of them is a girl. What is the probability that both are girls? And this is one of those questions that is somewhat misleading in my opinion. Because you might think if you weren't being very careful, you might think, well, one is a girl, there's a 50% chance the other one's a girl, there's a 50% chance of them both being girls. And that is definitely not the right intuition here, even though it feels like it could be right. So one is a girl. So that means we need to think about what our reduced sample space is. We're trying to find, if I call this A and this B, I'm trying to find the probability of B given A. That both are girls, given that one of them is a girl. So I could list my sample space, right? One of them being a girl, well, they could be both girls. They could be first a girl, then a boy, first a boy, then a girl. But they couldn't be boy, right? That's not a possibility of both of them. So I want to find the probability of B given A. It's going to be what I want, and B is just having both girls. Well, there's only one way of getting that out of the 3 total possible things. So we could just say it's 1/3. Or if we want to be a little bit more calculation based, we can say, well, it's the probability of B and A over the probability of A. Probability of B and A having both girls and at least one is a girl is both girls, which is 1 out of what? I see what you want to say. 4, right? There are 4. I didn't write them all down, right? But if you think about the actual total sample space, there are 4 possibilities. There's boy, boy, girl, boy, boy, girl, girl, girl. So that'd be 1/4 out of the probability of A that you have 1 girl is 3/4. I don't love saying 1 is a girl here. I'd probably like to say that at least 1 is a girl, because I feel like 1 is a girl, you might interpret it as exactly one of them is a girl. But obviously that's not the case here for asking what's the probability that both are girls. Just sometimes the language can be a little confusing, so be careful. Be sure to read things carefully. This reduces to 1/3. Now, the problem changes a tiny bit if we ask the same sort of question, but we have a family, still has 2 children, and we know that the oldest child is a girl. Now, what's the probability of both girls? And now the answer is 1/2, because there's only 2 ways the oldest child can be a girl. You either had a girl first and a girl second, or a girl first and a boy second. Those are the only ways the oldest child can be a girl. And so then if we want both girls, well, the probability of both girls is going to be 1/2. So if we're calling this A and our B is still just girl, girl, the probability of B given A is 1/2. Or 1 out of 4 divided by 2 out of 4, if you like doing it that way. So yeah, I'm really a fan of kind of this idea when you're doing conditional probability of thinking of your reduced sample space as your new sample space. So when I was calculating this, I was really thinking of this one here, right? That's everything I've got, at least in the conditional probability sense. And then this is what I want. Let's ask one more thing here. So in this 2 children situation, I want to ask a slightly different question. So we'll go back to this 2 children situation. And I want to ask, what's the probability of having at least 1 girl? This is kind of an easier question, which we already kind of calculated. That's going to be 3/4, because you can have girl, 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 boy, or boy, girl. And then we can see the probability of no girls. That looks kind of funny. Probability of 0 girls is just the probability of having boy, boy, which is going to be 1 out of 4. What I want to say is that these events, which I should have given names to, I'm so bad. I'm sorry. I'm really bad at giving my events names because I really don't enjoy doing it. What I want to point out here is that A and B are complementary, which means together they make up the entire sample space and they have no overlap. They are disjoint. They are mutually exclusive. So we have 2 things here. A and B are mutually exclusive, also known as being disjoint, which means mathematically or setwise, that the intersection of them is empty. You write as that's a symbol for the empty set. Some people do write their zeros that way. Another way of writing this is the set containing nothing. It also means that A and B are the entire set together. So that A union B is the entire sample space, omega. Here's what I want to point out. Being mutually exclusive and being independent are not the same thing. In fact, they are mutually exclusive. If you are independent, you can't be mutually exclusive, and if you're mutually exclusive, you can't be independent. Think about it this way. If I call this A and this B, what's the probability of A given B? So if I had boy, boy, what's the probability of having at least one girl? If I know I had two boys. Well, it's the probability of A and B divided by the probability of B. But if these two events are disjoint, what's the probability of A and B? It's nothing. It's 0 divided by whatever the probability of B is, which is 1/4, which is 0. So if the probability of A given B is 0, that's not going to ever equal the probability of A. So if two events are mutually exclusive or disjoint, they can't be independent. Because knowing that one of them has happened automatically means you know something about the probability the other one happened. Because it's 0. But I want to make that clear because it's something that people get confused a lot of the time. So independent is not the same. In fact, it's totally different than being mutually exclusive. And in fact, if you know one of them is true, you know the other one cannot be true. So if two events are independent, they cannot be mutually exclusive. If two events are mutually exclusive, they cannot be independent. It's kind of cool. All right, should we go that way? Maybe we should. Yeah. Okay, so typically, yeah, we should do that. Cool. There's definitely questions like this. So where this all typically kind of leads us to, and I know alluded to this a while ago, is kind of the disease testing stuff. Like you've got some disease, you want to test for it in the population, you know, the test positive a certain amount of time, and we want to know various things. So let's look at this example. Sorry, I've got my notes over here because I forgot to print them out. Well, I didn't forget to, I just did, but then I missed the paper. So let's look at this example. Let's say we have a blood test for a disease. And this test shows a positive result in 98% of the cases where the disease is present. By the way, if I was reading this question, at this point I would say, okay, D is disease, plus is having a positive test. And so far what this is saying to me is the probability of having a positive test given that someone has the disease is 0.98 or 98%. Right? So they're definitely telling us a conditional probability. It's the probability of having a positive test given that the person already has whatever this disease is. Okay. In 6% of the cases, where the disease is not present, we also get a positive test. So that to me says the probability of a positive test given that someone does not have the disease, which is the complement of having the disease, is 0.06. Finally, we're going to assume that the prevalence of the disease, meaning the probability of someone having the disease if they're just picked randomly off the street, is 20%. 20%? Oh no, not 20%. Sorry. 1 out of 250. Definitely not 20%. Much lower than 20%. So let's ask some questions. Well, actually, let's write that down. So that means that the probability of D, which is having the disease, is 1 out of 250, which is not 4%, it's 0.04%. Or sorry, 0.4, neither of those, 0.4%. Which is 0.004. I think. Yeah. Okay, cool. Yeah. I'm like, 1 out of 25 is 4%. So 1 out of 250 should be 0.04. 0.4%. I keep on adding to 0 there. 0.4%. So 0.004. And then just by complements, the probability of not having the disease should be 1 minus 0.004, which is 0.996. So now let's ask some questions. So when you see a question like this, though, I really encourage you to, as you read it, write down these things that we see, because they're definitely going to be there and we need to know them. So first and foremost, what's the probability that a random person will test positive? Well, there's a couple ways to do this. Well, I feel like I said all the time. There's always a couple ways to do it, depending on how you want to look at it. Both of the ways are kind of the same. They just look a little different. I think I would recommend using what we typically call a tree. So first, I pick a person. And usually in your branches, if you're doing branches, the branch you want to happen first is the thing that's like the given thing in your conditional probability. So if I'm branching, I can either do having the disease or not having the disease first, or testing positive or testing negative first. But it makes more sense to do the having the disease or not having the disease, because the branches after that will be conditional probabilities based on having had the disease or not having. So I'm thinking my tree should look like this. The first branch being the person either has the disease or does not have the disease. And then I'm also going to write the probabilities of having a disease. Maybe I don't need to. I'm going to. 0.004, 0.996. And then from each of these branches, we're going to branch again. If you have the disease, you can either test positive or test negative. The probability of testing positive, given that we have the disease, is 98%. The probability of testing negative, given that we have the disease, has to be what? Yeah, 2% or 0.02. Each branch, the probabilities have to add up to 1. There is no other choice. One thing happens or another. Maybe you have more than 2 branches, right? You have like 4 branches, and all those branches would have to add up to 1, but all the branches have to, in each branching, have to add up to 1. And then if we don't have the disease, we know the probability of having a positive test is 6% or 0.06. And if we do have, the probability of a negative test is the remaining part, which is going to be 94%. So the probability of the person testing positive is all the ways to get to positive. So the probability of a positive test is going to be the probability that someone has the disease times the probability of a positive test given that they have the disease. That's one way of getting there, like this. Plus the probability that they don't have the disease times the probability of a positive test given that they don't have the disease, which is this path here. Which, if we calculate, ends up being 0.004 times 0.98 plus 0.996 times 0.06, which ends up being approximately, wrong thing here, 0.0638. So picking a person at random off the street, there's about a 6% chance that they're gonna have a positive test. Now, if you think about this in this particular context, this makes sense. Most of the people you're gonna pick up off the street don't have this disease, right? 249 out of 50 of them. And the chance of a false positive is 6%. So it makes sense that our positivity test rate for just picking anyone off the street is still gonna be pretty close to that 6%, because we're just getting a slight bump up from the actual people we're gonna pick up off the street who have these, who are also gonna test positive most of the time. This rule here for the calculating this probability is called the law of total probability. Trying to find all the things, you find all the different ways you can get it. Another way you might draw this with a picture. Say, this is your total sample space. And let me sure I draw this picture right. I'm gonna draw a little not proportional because there's a lot more people that have the not having the disease than don't. But let's say like, here's all the folks that don't have the disease, and here's all the folks that do have the disease. And here's our positive testers. So if I'm trying to find the probability of testing positive, I can either have the disease and test positive. That's what that is right there. Or I can not have the disease and test positive. That's what I have right there. That's how that calculation is working. I don't think you need to know this picture. I often, especially if you're doing these like disease problems, you typically almost always want to do a tree because the tree is what makes it accessible. Yeah. The other question that is interesting to ask that we usually kind of go towards now is, okay, well, assuming someone tested positive, what's the probability that they actually have the disease? In other words, what's the probability of the disease given that they have a positive test? And when I look at this, well, this is kind of the prime example of what's called Bayes' law or Bayes' rule or Bayes' formula, whatever you want to call it. It's you're given some conditional probabilities and you're kind of asked to find the opposite direction, right? We were given the probability of a positive test given that someone has the disease, or being asked to find the reverse, probably that someone has the disease given that there was a positive test. Luckily, we have all the things we need to calculate this already. So the probability of having the disease given a positive test is just the probability of having the disease and having a positive test divided by the probability of having a positive test. And this can all be still viewed from our tree. The probability of having a disease and a positive test is this 0.004 times 0.98. Or in other words, it's the probability of having the disease and then the probability of having a positive test given that you have the disease. That's the top part. The bottom part we already calculated. I'm going to write it again because I think it's worth writing, but it's just going to be this 0.0638 that we already calculated. But it's going to be the ways of having a positive test, which is either having the disease and having a positive test given that, plus not having the disease and having a positive test given that. That's the whole shebang. That's Bayes' formula. I don't think you should memorize this formula. Like it's maybe when you take stats, you should memorize it, but I don't know. I feel like the way of doing it with trees is kind of the better way of doing it. We can write it out though if you want to memorize it. But let's finish this part first. So calculating this, it's going to be, let's see, this top part here is our 0.004 times 0.98. And the bottom part is the same thing, 0.004 times 0.98 plus 0.996 times 0.06. And normally I just leave my answer like that. I do want to calculate it though, just to kind of get an idea of what this is going to be, and I don't actually have it written down. Let's see here. So we have, sorry, my favorite calculator of all time. 0.98 times 0.004. I'm going to divide that by 0.0638. Approximately 0.0614. This is an important result because what it shows us is something maybe against what people usually think. If someone said, I'm going to give you a test for a disease, and if you have the disease, there's a 98% chance of having a positive test. And then you had a positive test. You would think there was a pretty good chance you have the disease. That's not what the math actually shows us. The math shows us that not knowing anything else, if you have a positive test, there's really only like a 6% chance that you actually have the disease. So it's really, really kind of misleading. That's why there are a lot of false positives, because the words are escaping me. How prevalent the disease is in the population really is kind of the bigger factor as far as actually having the disease when you test positive. So that's kind of what's going on. That's why this is very, very different. So the probability of having the disease given a positive test is approximately 0.06144 versus the probability of having a positive test given that you have the disease is 0.98. Very, very different numbers here. Not that that's super important when you're calculating stuff, it's just good to be aware of as far as real life. Wow, it just worked a lot. Okay. Let's see here. Yeah. Sorry, this is a bunch of examples here. I kind of want to look at that. So I should ask you all, actually, is there anything that I'm missing or that you would like to see me talk about before I just keep going on and on and on? Which I'm happy to do. I'm looking at the homework to see if there's anything particularly. There's a lot of independence questions on this homework assignment. Let's look at some of those. I'm curious. Let's look at number. That's the question. Maybe did I not print this out right? Like my question looks really weird. I'm just reading one of these here. Maybe I'm reading it wrong. Okay, I'm gonna read question 10. Suppose that you have a batch of red and white flowering pea plants. Pea plants. The red flowering plants. Oh, by the way, so I imagine most of you know this biology stuff, but in case you didn't already get this handout, here is a handout for some counting. Probably some of you got this. Did you get this? Just like not everyone has played with cards their entire life. That one. Yeah. So there's also some biology stuff on the back, which I'm never a pro at, so that's why I was kind of thinking of it. So let's see. So we have a batch of red and white flowering pea plants. The red flowering plants are of a genotype CC or C. Well, I should write it down. So red is going to be dominant or dominant recessive. The white flowering pea plants, wow, are of a genotype little c. So white is going to be little c. All three genotypes are equally represented in the batch. You pick one plant at random and cross it with a white flowering pea plant. What is the probability of the offspring will have red flowers? Okay, so we're going to take one of these at random, and these are all equally likely. So we're going to pick a plant at random. So there's a 1/3 chance of capital C, Those look like lowercase, so let's draw my next one's bigger. There's a 1/3 chance of lowercase. There's a 1/3 chance of lowercase uppercase. And there's a 1/3 chance of uppercase. Or I should say recessive, dominant. And then we're going to cross that with a white flowering pea plant. So we're going to take one of these and cross it with a white one, which is lowercase, or recessive. What's the probability that the offspring will have red flowers? Okay, so if we do a white one cross a white one, it's going to be white, right? Because there's no way to get a dominant in there. So white is going to be white. So there's definitely, for sure, white with white is going to be white. And there's a 1/3 chance of that happening. And then if we take the uppercase red one, there's a 1/3 chance of having uppercase, sorry, that's red with white, but this is the uppercase with the lowercase. Then, well, if we draw the little Punnett square for it, we have CC. Oh, there's a 100% chance of getting a red one, which I might have guessed wrong because I've forgotten how biology works clearly. And then finally, if we do the other red one where it's uppercase, lowercase c, and the white one, which is lowercase, our Punnett square is going to look like this. Big C, little c, little c, little c. So you're going to get big C, little c, big C, little c, little c, little c, little c, little c. So let's say there's a 1/2 chance of getting a red one here. So it looks like we're going to have a 0 ways of getting a red one here. 1/3 times 1 way, 100% of getting here, plus a 1/3 times a 1/2 over here. For a total of 1/3 plus 1/6, which is 3/6, which is 1/2. So it looks like that one's going to be 1/2, which is not what the question. I thought I was picking one that was independent versus dependent, but I actually didn't because I read it up. Yeah, I'm curious. Does anyone know what problem 11 is saying? Here's what it reads when I look at it. A drug company claims that a new headache drug will bring instant relief in 91. Yeah, exactly. I'm looking at problem 11 on the homework assignment, and at least this other one that I have says 89, but it feels like it's missing something. I printed it out. Maybe I feel like the printouts usually are not problematic. What am I missing? Yeah, a drug company claims that a new headache drug will bring instant relief in 89. That's the whole thing that's written. Maybe I missed it. I guess I could log into Canvas and look at it. But even then, like, it doesn't seem like it's giving us enough information. I'm super curious. Let's find out. I can access. Let's see here. 17C, where are you at? I mean, when does the homework due? Okay, so you've got some time. Okay. Sure. Or sometimes some of the interesting characters don't print correctly. Still, I'm curious what that means. Let's see, assignments. Where are you at? Now let's take a look here. Problem 11. Drug company claims a new headache drug. Okay, oh wow, yeah, that really got cut off. Will bring instant relief in 91% of all cases. If a person is treated with a placebo, what happened here? That's interesting. There's a 23% chance that the person will feel instant relief. In a clinical trial, half the subjects are treated with a new drug, and the other half receive the placebo. An individual from this trial is chosen at random. What is the probability that the person will have experienced instant relief? Okay, that's still not an dependent question because I still didn't read far enough. But at least the question makes sense in this situation. Yeah. So it's worth exploring. So the interesting thing to me about this question is we have to assume that what their claim is true. right? We're going with the assumption that the drug company's claim is true. So the probability of relief, given that they're taking the drug, is 91%. And the probability of relief, given that they're taking the placebo, is 23%. Not bad. In the clinical trial, half the subjects are treated with the new drug and half are treated with the placebo. So the probability of the new drug being given is 0.5, and the probability of the placebo, why do they use a B for placebo? What's that? Yeah, I don't know. I was like, placebo. I don't know. Probably because I didn't want to use P. I'm already using P out here. But yeah, it seems weird that I would use that, but I did. So we can go with it. So that's the drug. That's the placebo. I like that placebo. Wow, really blurry. That didn't help. That's the button supposed to make it less blurry. Okay, there we go. All right. Okay. Probably being given a placebo is also 0.5. Normally, I would just kind of calculate it, but I want to show a little bit of the thought process. If we're trying to find the probability of instant relief here, well, again, this is a total probability calculation. It's all the ways you can have relief. You can either have instant relief because you were given the new drug times the probability of being given the new drug, or you can have instant relief because you were given the placebo times the probability of being given the placebo. And each of these are things we know how to calculate. It's going to be 0.91 times 0.5 plus 0.23 times 0.5. Which will be whatever half of this is, whatever half that is. Looking like what? 45.5% plus 11.5% to get you 57% probably, or 0.57, I think. Okay, let me actually read one of the questions I meant to read. Holy smokes. Okay. Lots of card questions I see here. Let's skip the card questions. We've done enough card questions for now. An urn contains 18 green balls and 11 blue balls. So we've got 18 green and 11 blue. All right. You take two balls out of the urn, one after the other without replacements. So remove two balls without replacements. A is the event that the first ball is green. B is the event that the second ball is blue. Are A and B independent? Logically, what do we think? If I take out a green ball, so I should, actually, no, logically, I don't know what to think. I was going to say, if you take out a green ball, then probably the blue ball is diminished or different, but that's not, but they're not asking the probability that the blue ball is first versus the probability the blue ball is second. So we actually, I think, do need to really calculate this to see if it makes a difference or not. So we need to calculate, and I really do think we should calculate the probability of B given A versus the probability of just B. All right, interesting times. So probability B given A. I have to imagine, because usually you have like more than one chance to answer these questions. You could totally just guess each of these, right? Like if you've got more than one chance, you could guess one thing. Right, but you have more than one guess, I would imagine, right? There's only two options for these, so just say if you shouldn't have, you should be, unless you only get one shot for each. Maybe you only get one shot. I don't know. Okay, 5 seems like enough to get it right. So actually, now let's take a look. Let's look at the problem. Was it problem 13? Oh, but there's like multiple questions on. So I see it's probably going to be like you got to get them all right. You don't say which. Okay, all right. That's smarter planning. So probability of B given A. probably the second ball is blue, given the first ball is green. So if the first ball is green, and I think we should do this the short way. If the first ball is green, we're left with 17 green and 11 blue. So knowing that that's what we're left with, what's the probability of a blue? Well, it's going to be the 11 out of 28. But there's 11 blue balls left out of 28 balls total. We could have also calculated the more complicated way, but I don't think we want to. Okay, probability of the second ball being blue, that's a little more complicated. Right, that's the second ball being blue. So the first ball, something happens. It's either blue or green. So what's the probability? So we have to kind of divide this up actually in each situation. So we're going to do first ball blue, and we're going to do first ball green. Okay, question.
I guess the first ball is green.
Yes.
Like understanding behind why we put green.
Sure. So let's yeah, we'll come back. So we can calculate this. So it's kind of, I think this is the understanding, right? So I mean, all right. So we've got our urn. Here's our urn. And here's our, I'm gonna divide it up this way. I'm gonna say I can use colors. I got colors. I've got my 17 green balls and then another 1 green ball. And then I've got my 10 blue balls and another 1 blue ball. Divide them up this way, just kind of, I'm going to take one of them out at a time, so I want to see what's left. So, again, A is the first ball is green. And B is that the second ball is blue. So if I take out, if A happens, I remove without replacement 1 green ball. So I take this 1 green ball. How many balls are left? Maybe 28 balls. So that's my new total sample space. After A happens, we have 28 balls. How many of them are blue? 11 of which are blue. So the probability of getting a blue ball from the remaining 27 total balls is 11 out of 27. On the other hand, the probability of getting just a blue ball, given we don't know what happens to the first ball, well, if the first ball is blue, then what's the probability of the first ball is blue? Oh, I should leave my picture, but my picture is good. Maybe. Look at this. Cool. So, what's the probability that my first ball is blue? 11 out of how many? How much was that? Yeah, 11 out of 29. And then we have to multiply that by the probability that the second ball is blue. So now there's a 10 out of 28 probability that the second ball is blue. Because the first ball we took out a blue one, there's 10 blue balls left out of 28 balls left. That's going to be 10 out of 28. And then the same sort of thing over here. If the first ball is green, well, there's a 18 out of 29 probability of getting a green ball on the first ball. And then the probability the second ball is blue is 11 out of 28. And the question we have to ask ourselves is this equal to that? Sure. So I'm just doing the same thing. So this P of B, this probability the second ball is blue, there's 2 different paths to get there. I can either take a path where the first ball is blue, and then the second ball is also blue. Well, has to be blue. First ball, so let's actually write this down, right? So this is the probability that the first ball is blue. And this is the probability that the second ball is blue. Whereas over here, this is the probability that the first ball is green. And this is the probability that the second ball is blue. First ball being blue, well, nothing else having happened, there's an 11 out of 29 total possibility of the first ball being blue. And then I take away a blue ball, there's 10 blue balls left. So for the second ball to be blue, there's a 10 out of 28 chance of that happening. Because there's 10 blue balls left out of the 28 remaining total balls. Or I could have first removed a green ball. There are 18 green balls out of 29 total, so there's an 18 out of 29 probability of that happening. And then after I take out one green ball, there's still 28 balls left, and 11 of them are blue. There's an 11 out of 28 chance of that second ball being blue if the first one's green. So now the question you have to answer is, are these the same? My guess is no, but I should actually calculate it just to be sure, because maybe something weird's gonna happen. So I'm gonna be careful here. I'm gonna say I've got 11 times 10, which is 110, plus 11 times 18, which is 180, plus another 18, all divided by 29 times 28. I don't really want to multiply that out. So what I've got here is, let's see, 290, 308, I think, divided by 29 times 28. And I'm pretty sure that's not equal to 11 over 28. But I guess I could check. So 11 over 28 is about 0.39. And 308 divided by is about, well, they're pretty close. It's closer than I thought it was going to be. But they're not the same. Good. So these events are dependent or not independent. Is actually the words that are used in your homework assignment. Interesting. And then I was about to say, what if we did with replacement? That's actually what the next question asks. Is what we do. So let's take a look and see what happens if we do it with replacement. I think that's an interesting question as well. So come on. Okay, so same situation. We've got 18 green balls and 11 blue. A is still the first ball is green. B is still the second ball is blue. So now we still want to check and see, are these independent? So is the probability of B given A equal to the probability of B or not? The only difference here is now we are working with replacement. So let's calculate what I think is the easier thing first. Let's find the probability of B given A. Probability of B given A is the probability of the second ball being green given the first ball is, sorry, second ball being blue given the first ball is green. Okay, so here's what's going to happen. You're going to take out the first ball, what's probably being green? It's, I don't know, it's what, 18 out of 29. And then you're going to put it back in. So we did it. The first ball was green, that happened. And now, after that happens, what's the probability that the second ball we pull out is blue? Out of how many? 29, exactly. Because the first thing kind of didn't really happen from our perspective, or from the blue ball's perspective. Right? All the balls are still in there. It doesn't really matter that the first ball was green, which is certainly indicative of a very likely result that these are going to be independent. But we should still check. So now, what's the probability of B that the second ball is green? Sorry, second ball is blue. Right, because whether the first ball was blue or the first ball was green, you put it back in. And then when you pull out the second ball, the probability of being blue is still 11 out of 29. So these are definitely independent. Independent. That's kind of a good question. Yeah, I like that. Ooh, question 14. I'm not going to tell you the answer. Well, I've already told you the answer to question 14. A and B are disjoint, and they both have positive probabilities. Are they independent? Definitely not. They're not independent because they're disjoint. They can't be independent. It is weird. Technically, they could be independent if one of their probabilities was 0, but it's super dumb. No one should ever ask you that question. Yeah. I don't like to say, rarely do I like to say that anything is always true when it comes to probability, because it just, there's so many possible weird situations that someone could come up with. Even the whole thing about disjoint and independent, that's almost always true, that if you have one, you don't have the other, but technically you come up with a weird situation where one of them has a 0 probability and then they're disjoint and independent, which is super annoying. So my answer is probably, it's probably true that when you're doing things with replacement, you get independence because the prior things that have already happened can't really affect the later outcomes. But I would hedge. Yeah. Let's see what else we've got here. There was something else. Oh yeah, I know what it was. Yeah, here's a good example. So let's look at this one. Papers everywhere. So let's say we've got the following. Back to kind of our paper. Can I get you to do the thing I want you to do? Maybe. The thing always looks way further right than it should to me. I'm like, why are you so? It's because of the world. It always messes with me. I'm like, okay, kind of move it over. Let's say we have the following. A study by the National Lung Society found that of 2,000 women, 680 were heavy smokers. 50 had emphysema. I can't spell emphysema. It's all right. Not a spelling class. And 42 had both. Meaning they had both emphysema and were heavy smokers. So the question that we're going to ask is, are these events independent? Are the events of being a heavy smoker and having an emphysema independent? Okay, well, this is a situation where we kind of are forced to use the version of testing for independence that I don't love, which is fine. We don't really have any conditional probabilities here, though, right? I don't. So if I say that A is being a heavy smoker and B is having emphysema, I don't know what the probability of A given B was. I mean, I could probably maybe find it. Oh, maybe not. I probably could. But the point here is that it's actually easier to go the other way. So I'm going to check, is the probability of A intersect B equal to the probability of A times the probability of B? Because those are the easiest things to calculate here. So what's the probability of A and B? of being a heavy smoker and having emphysema. Wow. How many people have emphysema and are heavy smokers? I think it's 42 out of how many? Yeah. So there's our probability of both happening, being a heavy smoker and having emphysema. 42 out of 2,000, which we could write as a decimal, I suppose, if we really wanted to. It's going to be 21 out of 1,000, which is 0.021. All right, how about the probability of A times the probability of B? Well, the probability of A, which is being a heavy smoker, is 680 out of 2,000. The probability of B, which is having emphysema, is 50 out of 2,000. And I'm pretty sure that those don't equal each other, but we can check. It's about, if you calculate this, is going to be about 0.0085. Those are definitely not the same. So no, they, I mean, I would expect being a heavy smoker and having emphysema are not independent of each other. We would think that they are dependent or related. So they're not independent. It says we don't usually say that things are dependent just because dependent kind of assumes maybe a causal relationship, and that's not really what we're trying to say. We're trying to say something more about how they're related or correlated, but they're not necessarily depending on each other. So usually we use the words not independent, so dependent. Yeah.
So just to clarify, for independence, we use either one of those three different.
Exactly. The two ideas are really kind of the same. It's probably A given B equals probability of A, or probably B given A equals probability of B. But yeah, this is kind of the other version. You could have done it this way if you really wanted to. If you wanted to find the probability of, say, like A given B, it's the probability of A intersect B divided by the probability of B. Probability of A intersect B in this situation, we calculated was 42 out of 2,000. Probability of B, which is given to us, which is having emphysema, is 50 out of 2,000. This ends up being 42 out of 50. And that's definitely not equal to the probability of A, which is 680 out of 2,000. But they really are the same calculation, because saying that this is equal to this, right, which would show that they're independent, it would be the same as if you multiply both sides by the probability of B and got probability of A intersect B equal to probability of A times probability of B. They're really the same calculations, it's a different way of seeing it. All right, 2:59. I guess we'll stop talking. I guess we can talk more about probability on Thursday if you all want to, or we could do some sort of review. I don't know, like I feel like since your final is going to be half probability, it might make sense to talk more about probability. But honestly, we can kind of do whatever you want. Yeah. I'll come prepared to talk about probability, but also, yeah, I'll look and see what I have as far as older stuff, because you probably want to remind yourselves of what happened before. Yeah. I think I do. I was just asking myself that same question. Let me take a look. It might not be on Canvas yet, but let me see if I do. We do have a final review on there. I wonder how suitable it is. Well, I'll take a look and we'll see. If this doesn't seem good or good enough, I'll look for other stuff.